So our next speaker is coming from the University of Washington. So Timothy Trinklein will be speaking about simulating GC GC-TOFMS data with realistic run-to-run shifting to evaluate the robustness of chemometric software. Timothy, the floor.
Can everyone hear me all right? Thumbs up in the back. Okay, cool. So I'm also going to be talking about simulation, but like in a totally different aspect and like philosophy, so to speak. So I was like thinking about looking for my cover slide, Dolly, you know, the AI software, and typed in these simulating GC GC chromatograms. This is on the hot. So I thought that would be a good cover to start with. And then, you know, PH inspired me when he was using ChatGPT the other day in his slides. And so I thought, you know, I couldn't think of what to put for my outline. And so I said, you know, why should I simulate chromatographic data? I figured maybe AI could tell me what the reason is. And the answer is not too bad, actually. It's like, okay, so you want to like test and optimize methods. You want to study underlying principles like I was talking about. What I'll talk about is like bullet point number 3, evaluating and comparing software. Number 4 is good too, providing training for chromatography personnel, like the simulators that Dwight has and things like that. Then of course you want to generate data for research, publications, and I guess patents too. So I'll focus on number 3, evaluating chromatographic software. And the specific chromatographic software I'm evaluating in this work is a tile-based F-ratio method that our group has made. So if you aren't familiar, basically it works like this. You have 2 or more classes of chromatograms of samples. We segment them into regions called tiles, which are basically a fancy way of binning things. We integrate the sample in the tiles as a function of mass channel, and then we compare them using the F-ratio statistic. So it's a multiple hypothesis test. We just figure out what are the differences using this, you know, very simple statistical measure. And then we get what's basically an initial hit. So it shows us in order of F-ratio, where are the regions in the chromatogram where things are changing. So high F-ratio means there's something going on here, low F-ratio means there's nothing going on. Okay. We get an initial hit list, and then we can go in more detail and say, oh, analyte 1, okay, that looks like a real thing. We can match it to NIST, say it's this. Analyte 2, that looks like some column bleed. We're just going to delete that from our list. Okay, so you can evaluate it. And then here's some recent work from our group as well as some others using this method. It's commercialized by Lico's Chromatograph Tile. This is what basically a hit list looks like, and how you can go and click on the different hits, say what they are. The right panel shows you the averages in different classes, and you can see, oh yeah, that peak really is different between class 1 and class 2. It's not just our imagination. And I was just talking about tiling in terms of F-ratio, but we've also been working in different ways to implement tiling as a chromatographic pre-processing method. So Caitlin just had a recent paper, and Grant was talking about this method yesterday, where let's say you just have 2 chromatograms and you want to find the differences, but you can't calculate statistics because there are enough replicates. Well, you can basically just take the area normalized difference. And then Paige, a student who just graduated from our group, she was looking at, well, what if the cases you don't have defined classes of samples, maybe you just have a bunch of samples, you don't know where they came from. Is there an unsupervised way to use this metric? So I just wanted to mention this. All right. But going back to simulating data and using simulated data to evaluate F-ratio analysis. So this is where the talk is kind of gory and boring and detailed, but basically these are the things we're going to use as parameters to simulate. So chromatographic saturation, if you've ever read like a Joe Davis paper, it's like, how complicated is your chromatogram? How many peaks do you have per peak capacity? Then the amount of run-to-run shifting, this is like the main thing we wanted to simulate and simulate it as realistically as we could. And we used this metric, we're going to call it del, which is the standard deviation and run-to-run time shifting per peak width. So how much is an analyte shifting per how wide it is, basically, on both dimensions. Background variance is an important thing. Maybe you're just running replicates of the same thing, you'll have low variance. Maybe you're doing a long time course metabolomic study, you have a lot of variance, so different cases. Okay, and then the tile size. So the whole point of doing simulations is to inform the user how to better use software, okay? And in terms of the specific software I'm talking about, the main thing the user has to optimize, and probably the most important thing, is the tile size. And I'm going to talk about it in terms of this metric of relative tile area. But you can imagine there's more scope to this. These are ways to simulate chromatograms, and maybe you want to use a different software package. It's not tile-based F-ratio or some other chemometric method. The whole idea is how do we inform the user how to make better choices about the software to get the most out of their data? Okay, so that's the overarching idea, the overarching motivation. So back to these three variables. The first one is saturation, and I'm showing 3 simulated GC GC-TOFMS chromatograms here. And the whole idea is we picked 3 saturation levels that we thought would be representative of 3 different experiment types. Okay, so the left-hand panel shows like alpha 0.1. That means you have 10 times more peak capacity than you have components. Maybe a simple sample of fragrance, there's still going to be coevolutions, but by and large, you can handle them and deal with them with, deconvolution software and so forth. The middle is maybe a more difficult metabolomics type experiment, alpha 0.5. There are a lot of things overlapping, but this is usually what we have to deal with. Even with 2-dimensional separations, a lot of things still coalute, right? It's this complicated sample. And then we thought, let's turn the dial to 11. Alpha 2.5 is it's just a wall of peaks. You can't really see anything. Usually our separations don't look like this, or hopefully they don't, but the idea is maybe in a really complex separation, if you zoom in, maybe like the aliphatic region of diesel or something, there is crazy overlap like this. And the other point was just to see, can we drive this to its breaking point? How far can we go? Okay. This is looking at the RSD within class. So the left-hand panel, injection limited case. You have maybe you spike something, and then you have another sample, okay, and you're just looking at injection variance, how much variance in volume the syringe injects, okay? So it's not so much. The right-hand case is what you probably are dealing with in a real study, you have real samples, okay? So you have a lot of variance, either just from instrument drift, or you have subclasses in your data, your different samples are different, real hard experimental variance, okay? And so I made it as, I'm going to call it a synthetic test mixture. It's got a bunch of mass spectra from NIST, okay? This is just showing how different the mass spectra are in this simulation, okay? So some peaks are similar to each other, some are different, okay? And then basically in each simulation, I would take 20 analytes and then I upregulate them by a factor of 2. And the whole point is to see how well we can discover these analytes that are changing, that are statistically meaningfully changing, okay? Some more gory simulation type stuff, okay? On the left-hand side is a peak area distribution. So in real life, you have a real sample, not everything's the same concentration, right? They follow usually an exponential or exponential-like distribution of concentrations. And then I kind of fix that to even have a no more than a 10 to the 3 variance, because even if you have concentrations of a dynamic range of 10 to the 8, well, even a TOF can't measure that dynamic range, so it's a bit smaller, okay? The other thing we thought was interesting is how do we put noise in the simulation, right? Because if you just have pure peaks, it's going to work perfectly, right? If you have no noise. And so we thought, well, let's just keep adding more and more and more noise until this thing totally crashes, okay? And then let's take a step back right before it crashes. That's how much noise we're going to put in. So that star there is right before everything just fails. So we're putting a lot of noise in these simulations to try and make it pretty realistic and pretty challenging. This shows a couple analytes. The left one is a super intense peak, a beautiful analyte. You see a bunch of mass channels in that top left-hand panel. I mean, you can just click on it and say, oh, NIST says it's this species, works perfectly. But often we don't have that case. The right-hand panel, here's an analyte. You see there's a couple mass channels in the top hand right that are peeking out. And the bottom right panel, there's a concentration difference, and we can measure that. We can't identify it. And that's something that's interesting, right? A lot of times in non-targeted analyses, you can discover more things than you can actually identify if you're really looking at the low signal to noise things. And a lot of times people just truncate all these analytes away and they don't find them. But it's something that's worth looking into. Okay, so the main thing we were really interested in studying was how to simulate retention time shifting, run-to-run shifting, which is the hardest thing we have to deal with, I think, in terms of 2D GC, and I think LC people have it even worse. But we looked at an old data set of yeast, and this was a several months time course study. So we had a lot of run-to-run shifting in this data set. And we said, well, let's pick out 10 analytes and let's look and see how they actually shift. How do they shift and what do they do? Here's an example. This is cystathionine. I'm just showing you a little zoomed in picture of where this analyte is, and you can see it's bopping all over the place. It's doing crazy stuff, okay? So that's just one analyte though. And we can measure how much that one analyte is shifting, okay? But we need a big picture of how do all the analytes shift over the course of the whole separation, right? Okay, so we came up with these things called shift functions. And so each dot on that line is a different analyte. And we fit a function to see how do analytes shift as a function of retention time, function of runtime, okay? in chromatography, we're at the mercy of low frequency flicker noise, right? Slow changes in gas, changes in temperature, changes in flow, all these things are low frequency, and they are really what kind of the Achilles heel of a lot of chromatographic methods. But what we see is there are a few maxima in these curves, kind of regions where peaks are all shifting on one way, and then they start shifting backwards a little bit. So these kind of low frequency changes in how these things behave. This is 1D. We also looked at the second dimension. The second dimension behaves very similar. It's just a fast separation, right, in 2D of GC, so we shouldn't expect it to be that different. So then we have this idea of how shifting behaves, and the question is, how do we simulate that, okay, in a realistic way? So the top left-hand panel is like, okay, let's just randomly distribute peaks into a 2D space, okay? So this is like using a lot of methods of like old school statistical overlap theory to kind of drive our motivation. We're just throwing a bunch of analytes randomly into space. And then in the top right shows a shift function we need. So basically, we're trying to simulate a function that looks like these functions we have from real data. Okay. And so, you know, there are a couple maxima on those real functions. And so all I really did is let's take some white noise, some Gaussian white noise, apply a low pass filter. And so we have this low frequency waveform with a few maxima, a few minima. Okay, not too many. And then if we want things to shift more, we can just vary the amplitude of that function. Okay. And then the bottom set of slides that shows we're going to do it for every single run. We're going to make a new function, okay? And then we're going to map the analytes onto that function, and that's how they're going to shift. The whole reason is if you just treat each analyte individually, it's not realistic because analytes shift together with each other as those low frequency changes in flow and temperature occur, okay? All right. Just taking a look at an individual analyte, okay? So the top left, no shifting, okay? That's what we would like to happen, but that's not reality. Top right, this is del of 0.5, which means that we're having an analyte shift by about half of its width, okay? Bottom left, we're having an analyte shift by a whole peak width. Bottom right, we're having an analyte shift by 2 peak widths, okay? Like, can we deal with these amounts of shifting in real data? So with chromatograph tile and other tile-based methods, we have the tile size. The user gets to pick that. You get to decide how big do you want your tile to be, okay? So there's a, you know, some person might have like a really high peak capacity separation with really narrow peaks, and somebody else might be doing a long, big chromatogram with big peaks. So how do we make our results generalizable to any situation? So we came up with this relative tile area thing, which is basically just how big is a tile relative to the peak. So it's generalizable, okay? And SCP is like a single component peak. It's like an old term. So this is just a picture of what that means. That's how big our tile is in pixels. And then we have this example peak here. And if you just take tile area over peak area, you get about 6.25. I made that fraction upside down, but you get the idea. Okay. We studied 7 tile areas from the whole spectrum. So what if our tile is like smaller than a peak? Like, will the software still work? And then what if our tile is like way, way bigger than the peaks? Will it still work? So, I mean, think in the case of like, if the tile is just the size of the peak, you should probably get good results if there's no shifting in the data. And then if your tile is way, way bigger than your peak, then you should be able to take care of that retention time shifting, but at a cost, because you're going to be integrating things that aren't shifting around. You might be integrating multiple analytes at once, and so there's a trade-off. And we wanted to study the whole spectrum of cases. All right, so those are all the parameters we're simulating. How does this get put together into an experiment? Okay, so we're going to take a bunch of combinations of those conditions. We're going to take a given amount of saturation, a given amount of RSD, a given amount of shifting. We're going to simulate 20 experiments. Each experiment will have 6 runs, and we're going to change 20 analytes and just see if we can find them. Okay. So we take what I'm going to call a simulated class-based experiment, just a bunch of simulated chromatograms, throw it into the software, and then because we know where we simulated all the analytes and we know what they all are, we can go in and say, how well did it work? How many of these things that the software found are true positives, analytes we really simulated, and which one of them, which hits are just like noise, like, you know, like things that arose from shifting and noise, not really hits. And from the information, we can make a ROC curve. And I love ROC curves because they're super informative. And basically, a ROC curve of 1 means, boom, you got all your analytes are at the top, super successful. A ROC curve area of 0.5 means you're just flipping a coin, you're getting analytes, you're getting noise, who cares, okay? So later on, I'm going to use this area under the ROC curve as a proxy for discovery success. Basically, if you have a ROC curve area of 1, you're doing great. And when that number gets lower and lower and lower, it means they're not doing a very good job at discovering things, okay? So we'd like to see something like this when we go on our hit list and look at an analyte. We'd like to see a tile, top left is bigger than our analyte. And if the analyte's shifting around, like in the top right, we want that tile to integrate over that whole area so that the effective shifting is nullified. And we're just integrating the peak areas and not, you know, things that arose from shifting, okay? And the bottom two parts of this just show projections, you know. This is how the shifting is happening on the first dimension, the bottom left. This is how the shifting is happening on the second dimension on the bottom. Okay. So this is the result, and it's a really complicated slide, and I'll distill it down in the next few slides. But basically, you know, the top right, we're looking at the low alpha increasing left to right, low RSD. Bottom is showing you the high RSD cases. But there's a lot going on here, so let's try and distill this down. So I'm just zoom in on number A here and kind of like, well, let's see what's going on here. So this is A. This is low alpha, so a simple separation where you don't have that many coelutions. Low RSD, so basically, you know, just injection variance, okay? And then we have all our levels of shifting as different traces on here. And the y-axis is the area under the rock curve. So again, 1 means perfect, discovery, 0 is bad. And then the x-axis, we're increasing our tile size, okay? And so I put stars here for each line, for each amount of shifting where the best tile size is. So if there's no shifting in your data, you can use the tiniest tile size you can imagine, okay? And then you'll get the best results. And as you increase the tile size with no shifting, it hurts a little bit, but not that much. Maybe it takes a little bit longer to do the study, but it's not a big deal, okay? Now, if you go down the traces with more and more shifting, so for instance, the diamonds delve 2, that means your analytes are shifting like 2 picoids, a huge amount. It makes sense. You need a bigger tile to integrate over those analytes to sum up and nullify the shifting. Okay, that's kind of a logical result. Okay, so that information for all those plots is distilled here. Okay, so the y-axis is the tile size relative to tile area, and the x-axis is the amount of shifting you have in your data. And it makes sense. As you have more shifting, you need a bigger tile size. Okay, that's a pretty obvious conclusion. We found something else interesting, though, which is that if you see all the red traces, all the red markers, which are the high RSD case, they're all above the blue markers, which are the low RSD case. So something that's a little less intuitive is that if you have a study where you have a lot of variance, like a time course metabolomic study, it turns out a tile size, a bigger tile size is better than a smaller tile size compared to a data set with much less variance. So not as intuitive, but kind of an interesting observation. So here's another distillation of results. This is all kind of the maxima from that really nasty plot a little bit ago. And so the left-hand plot here is showing the alpha 0.1 case. And each dot is just the rock curve area at the best tile size. So let's say you did your study well, you picked the best tile size you could. What are the results you're going to get? So this is basically best case scenario. What's going to happen, okay? And the blue dots are going to be the low RSD and the red dots are the high RSD, okay? And so most of the trends make sense, okay? So the left-hand case, if you have a simple sample, you know, even if you have really complicated studies where you have a lot of variance and things, okay, you can still do pretty well and discover most things. In the middle case, RSD starts to be a little bit more painful. You see those red dots dipping down a bit, okay? And in the right-hand case, the extreme case, obviously it's not working as well. But what is interesting is that if you have almost no shifting, that top blue dot, you can almost discover everything. So that was kind of a surprise. It's basically saying you can have an insanely complicated 2D chromatogram, but if you don't have any shifting, you can still discover most things. So there's a lot of interplay between these different sources of noise, okay? So if you can kind of trap down one source of noise in your study, then the other ones aren't so bad. And the mass spectrum can help you a lot. But from this results, basically, I mean, you can't put lipstick on a pig. If you have shitty data, you're gonna get shitty results, okay? So that's kind of the result, okay? So motivation for people to design studies as best we can. Of course, we're always trying to do that, but you know, sometimes we make mistakes and don't get the best results. So today I talked kind of about simulating chromatograms with a bunch of different parameters we thought would be interesting to study, like saturation, noise. And we wanted to make it a challenging test for chemometric software. And we didn't want to do something that we knew would work because we wouldn't learn anything, okay? But I just talked about tile-based F-ratio analysis, using these simulations to help people pick the best tile size for a tile-based analysis. But the point I want to make is a lot of these things that we looked at, how to simulate shifting realistically, how much saturation to put into peaks, all these things are put in the simulation. This could be applied to other chemometric methods. So you could compare ParaFac and ParaFac 2, okay, like James does. And we know from ParaFac 2, you can handle shifting a bit better. Okay, we haven't done this, but these are applications. These are reasons why you might want to bother simulating stuff, okay? So that's my spiel on simulations. Thanks for staying awake. Let me know if you have any questions, and I'd be happy to answer them.